Today's lesson is called Glacial Theory and the Quaternary. This lesson introduces the big picture behind glaciation. Before we can understand how glaciers move, erode, and shape landscapes, we need to understand when and why large areas of the Earth became covered in ice. The key period we are studying is the Quaternary Period, which is the geological period we are living in today. During this lesson, we will explore how Earth's climate has changed between cold and warm phases, how ice spread across the British Isles, and why these long-term climate changes happen. The big question for today is, why has Earth's climate repeatedly shifted between icy and warmer conditions? By the end of today's lesson, you should be able to identify the main characteristics of the Quaternary Period. You should also be able to explain the difference between glacial and interglacial stages. We will then look at Milankovitch cycles, which help explain long-term natural changes in Earth's climate. Finally, we will trace the maximum extent of ice across the British Isles and consider how glaciation affected the landscapes we see today. So today's lesson moves from the global scale, looking at Earth's climate system, to the regional scale, looking specifically at Britain under ice. Before we go further, let's define our key vocabulary. The first term is quaternary. The Quaternary is the current geological period. It began around 2.6 million years ago and continues to the present day. The second term is glacial. A glacial is a cold stage during an ice age when temperatures fall, glaciers expand, and large areas of land become covered in ice. The third term is interglacial. An interglacial is a warmer stage between glacials. During an interglacial, temperatures rise, ice retreats, and sea levels rise. The fourth term is accumulation. Accumulation means the buildup of snow and ice, usually at the head or upper part of a glacier. These terms are important because they help us describe climate change over very long periods of time. A weak answer might say, the Earth got colder and then warmer. A stronger answer would say, during the Quaternary, Earth experienced repeated glacial and interglacial stages, causing ice sheets to expand and retreat. Let's begin with a question. What if London was buried under 1 kilometer of ice? That might sound like science fiction, but during parts of the Quaternary, large areas of the British Isles were covered by ice. Around 20,000 years ago, during the last glacial maximum, much of northern Britain was buried beneath ice. The Quaternary is defined by these huge shifts in climate. At times, Earth was much colder than today. Ice sheets expanded across continents, sea levels fell, and landscapes were dominated by glaciers, permafrost, and tundra. At other times, including today, the climate was warmer. Ice retreated, sea levels rose, forests expanded, and human societies developed. The slide also tells us that the Quaternary is sometimes called the Age of Humans. This is because our species evolved and became dominant during this period of extreme climate change. That means the Quaternary is important for both physical geography and human history. It shaped landscapes, ecosystems, sea levels, and the conditions in which humans lived. Let's answer a question. Why do you think studying past climate change helps us understand the world today? Here's the model answer. Because it shows that Earth's climate has changed before, but it also helps us compare natural climate cycles with modern human-caused warming. Now let's place the Quaternary on the geological timescale. The Quaternary period spans the last 2.6 million years. It is divided into two main epochs. The first is the Pleistocene. The Pleistocene is often called the Ice Age. It lasted from the beginning of the Quaternary until around 11,700 years ago. It was characterized by repeated glaciations, meaning ice sheets expanded and retreated many times. The second epoch is the Holocene. The Holocene is the last 11,700 years of relative warmth. This is the interglacial period we are living in now. So, when people say the Ice Age, they often mean the Pleistocene. But it is important to understand that the Ice Age was not one single period of constant ice. It was a series of colder and warmer phases. During colder glacials, ice expanded. During warmer interglacials, ice retreated. This cycle happened repeatedly during the Quaternary. Let's ask a question. What epoch are we living in today? Here's the model answer. We are living in the Holocene, which is the current warm interglacial. Now let's compare glacial and interglacial periods more clearly. During a glacial period, temperatures drop. Because temperatures are lower, more snow survives through the summer. Over time, snow builds up, compacts, and forms ice. Ice sheets and glaciers expand across large areas of land. At the same time, sea levels fall. Why? Because large amounts of water are locked up on land as ice. Water that would otherwise be in the oceans is stored in ice sheets and glaciers. This lowers global sea levels and can expose land that is normally underwater. During an interglacial period, the opposite happens. Temperatures rise. Ice sheets and glaciers retreat. Meltwater returns to the oceans, causing sea levels to rise. Coastlines shift, habitats change, and ecosystems expand into areas that were once covered by ice. We are currently in an interglacial called the Holocene. This distinction is very important. Glacial equals colder temperatures, ice expansion, and lower sea levels. Interglacial equals warmer temperatures, ice retreat, and higher sea levels. Let's ask a question. Why do sea levels fall during glacial periods? Here's the model answer. Sea levels fall because more water is stored on land as ice, so there is less water in the oceans. Let's check your understanding. Which of the following describes an interglacial period? 1. A period when ice sheets cover most of the planet. 2. A warm period between glacial advances. 3. A period when sea levels are at their lowest. 4. The name for a specific type of glacier movement. Choose your answer now. The correct answer is option 2, a warm period between glacial advances. Option 1 describes a glacial period, not an interglacial. Option 3 is also linked to glacial periods, because sea levels are lowest when more water is stored as ice. Option 4 is incorrect because interglacial is a climate stage, not a type of glacier movement. So remember, interglacial equals warmer period between glacials. Now let's zoom in to the British Isles. During the Devensian, which was the last major glacial stage in Britain, ice reached as far south as the Bristol Channel and the River Thames. Northern England and Scotland were completely buried beneath ice. Southern England was not covered by thick ice in the same way, but it was still extremely cold. It was a periglacial environment. Periglacial means an area near the edge of ice sheets. These places were not necessarily covered by glaciers, but they experienced freezing conditions, permafrost, and strong cold winds. Imagine Britain at this time. Much of Scotland, Wales, and northern England would have been covered by ice sheets and glaciers. Further south, the landscape would have been tundra-like, with frozen ground, little vegetation, and harsh winds. This glaciation shaped the landscapes we still see today. Places like the Lake District, Snowdonia, and the Scottish Highlands show evidence of past glacial erosion, including U-shaped valleys, corries, arêtes, and ribbon lakes. So, although Britain is not mostly covered in ice today, many British landscapes were created by ice during the Quaternary. Let's answer a question. Why is the Lake District an important place for studying glaciation? Here's a model answer. Because it contains many landforms created by past glacial erosion, such as U-shaped valleys, corries, and ribbon lakes. Now we need to ask a bigger question. Why does Earth's temperature change over long periods of time? One important explanation is Milankovitch cycles. Milankovitch was a scientist who showed that Earth's orbit and tilt change over thousands of years. These changes affect how much solar energy different parts of Earth receive. There are three main cycles. The first is eccentricity. Eccentricity means the shape of Earth's orbit around the Sun changes. Sometimes the orbit is more circular. At other times, it is more oval. This affects the distance between the Earth and the Sun during parts of the year. The second is obliquity. Obliquity means the tilt of Earth's axis changes. Earth is tilted, and that tilt is one reason we have seasons. When the tilt changes, it affects how extreme the seasons are. A greater tilt can make summers warmer and winters colder. A smaller tilt can make seasons less extreme. The third is precession. Precession means the Earth wobbles slightly on its axis, a bit like a spinning top. This changes the timing of seasons in relation to Earth's position in its orbit. These cycles happen over thousands to tens of thousands of years. They do not explain day-to-day weather, but they do help explain long-term patterns of glacial and interglacial stages. The key idea is that changes in Earth's orbit and tilt alter the amount and distribution of solar energy reaching the planet. If summers in high latitudes are cooler, winter snow is less likely to melt. Snow can survive year after year, leading to accumulation and eventually glaciation. So, Milankovitch cycles help explain why ice sheets have expanded and retreated repeatedly during the Quaternary. Ask students, why are cool summers important for glacier growth? Model answer. Because snow from the winter is less likely to melt, so it can build up over time and eventually form glacial ice. Milankovitch cycles are not the only natural influence on climate. Solar activity also plays a role. The sun does not always release exactly the same amount of energy. At times, solar output is slightly higher. At other times, it is slightly lower. One sign of solar activity is the number of sunspots. Periods with fewer sunspots can be linked with lower solar output and cooler global temperatures. The slide gives the example of the Little Ice Age, which lasted roughly from 1300 to 1850. This was not a full glacial period, but it was a cooler period in recent history. During parts of this time, winters in Europe were severe, and the River Thames in London sometimes froze so solidly that frost fairs were held on the ice. This helps us understand that climate can be influenced by different natural factors. However, it is important to separate short-term or smaller-scale cooling events, like the Little Ice Age, from the much longer glacial interglacial cycles of the Quaternary. Let's ask a question. Was the Little Ice Age the same as a glacial period? Here's a model answer. No. It was a cooler period in recent history, but it was much shorter and less extreme than a full glacial period. As ice retreated at the end of glacial periods, it did not simply disappear without leaving a trace. Glaciers reshaped the Earth's surface. They scoured the landscape, carved deep U-shaped valleys, created lakes, and deposited huge amounts of sediment. The Lake District is a good example. Many of its valleys and lakes were shaped by glaciers. The transition from the Ice Age to today changed habitats dramatically. Areas once covered by ice became lakes, forests, grasslands, and eventually places where people could settle, farm, and build communities. So the Quaternary matters because it explains why many landscapes look the way they do today. When we study glaciation, we are not just studying ice. We are studying the history of the land beneath our feet. Now let's check the scale of these climate influences. You need to place these influences from the longest time cycle to the shortest. Solar sunspot activity, eccentricity, obliquity, precession. Think carefully. Which changes happen over the longest timescales and which happen over shorter cycles? Write down your order now. The correct order from longest to shortest is 1. Eccentricity, which is the change in Earth's orbital path. 2. Obliquity, which is the change in Earth's tilt. 3. Precession, which is the wobble of Earth's axis. 4. Solar sunspot activity, which happens over shorter cycles. This helps us see that different climate drivers operate over different timescales. Some influence climate over tens or hundreds of thousands of years. Others operate over much shorter periods. Now we come to a more challenging question. The Quaternary is defined by cycles of ice and warmth. So, if human activity is warming the planet, have we stopped the next glacial period or just delayed it? This is a difficult question because it involves both natural climate cycles and human-caused climate change. Naturally, Earth would be expected to continue moving through glacial and interglacial cycles. However, human activity has increased greenhouse gas concentrations, especially carbon dioxide. This has raised global temperatures and changed the baseline conditions of the climate system. As a result, some scientists argue that human activity may delay the next glacial period by thousands of years. Others argue that human influence is now so powerful that we may have entered a new period called the Anthropocene, where human impacts are a major force shaping Earth systems. The important point is this. Natural climate cycles still exist, but human activity is now strongly influencing climate as well. That means the future of the Quaternary may not follow exactly the same pattern as the past. Here is a discussion question. Do you think human activity is now more important than natural cycles in shaping the climate? 1. You might have said that global warming may delay the next glacial inception by thousands of years. You might also have said that human carbon dioxide emissions have disrupted natural ice accumulation cycles. Another strong point is that future cooling caused by natural cycles may not be enough to trigger large-scale ice formation if baseline temperatures remain too high. The strongest answers recognize both sides. Earth has natural climate cycles, but human activity has now become a major influence on the climate system. To summarize today's lesson, the Quaternary Period began around 2.6 million years ago and continues today. It includes repeated glacial and interglacial stages. During glacial periods, temperatures fall, ice expands, and sea levels drop. During interglacial periods, temperatures rise, ice retreats, and sea levels rise. We are currently living in the Holocene, which is a warm interglacial. The British Isles were heavily affected by glaciation during the Quaternary, especially during the Devensian. Milankovitch cycles, eccentricity, obliquity, and precession help explain long-term natural climate change. Solar activity can also influence climate over shorter timescales. Finally, human activity may now be disrupting or delaying the natural glacial-interglacial cycle. Next lesson, we will move from theory to processes. We will look at how glaciers move and how they erode the land.